So welcome. So we're going to move on and do DC circuits now. So DC stands for direct current. AC stands for alternating current. You can have a DC voltage, direct current voltage. It's just DC is what we use for when it's like a non-alternating thing. Let's have a look. We're going to talk in terms of series and parallel resistors. We talked about series and parallel capacitors before, so we're going to talk about that. We're going to talk about combinations of resistors, like we did about combinations of capacitors. Then we're going to talk about simple circuits, and this is like I feel like I'm rubbing salt into the wound here, because simple circuits tends to be a skill that only comes with a fair amount of practice. The equations are simple, but the analysis is not. So don't be fooled by simple. It does not mean simple. And then we go to a more complicated analysis for more complicated circuits, which is Kirchhoff's rules. And that, because it's much more formulaic, it's much more, you're following a routine, tends to be answered better. Actually, it's kind of interesting. And then we apply a little bit of this to capacitors, and at the end we'll be getting the DC effect in time of a voltage on a capacitor. So that's where we're ending up going, and we end there. So different bits. Maybe 3 skills, maybe 3 or 4 skills in here. So let's start talking about series and parallel bits. If you, like me, were introduced to this whole area through resistors, you know these ones better than you know the capacitor ones. If you were introduced to this through capacitors, then you probably know the capacitor ones better than you know these. The important thing to realize is that the rules are opposite. So whereas for capacitors, the simple bit was adding together parallel capacitors because the area is just added. So we said CP equals C1 plus C2. We've got to do the inverse for this. And I actually prefer putting RP and RS, because you might as well remind yourself I'm talking about series or parallel. So 1 over RP equals 1 over R1 plus 1 over R2. And for the series combination, it is, whereas before we learned 1 over C series equals 1 over C1 plus 1 over C2, etc., etc. Now it's RS is equal to R1 plus R2. And if you think about it, if I imagine how hard it is to blow through a single straw, and I compare that with blowing through 2 straws stuck end on end, it's going to be harder. Because I've got to blow through the first, then I've got to blow through the second. So my resistance to me blowing will get higher. So the only way I can do that is by adding the 2 numbers together. If I have imagined the resistance of blowing through 1 straw, and then I put the second straw beside it in my mouth, so I have now 2 straws to blow through, the resistance is less. How can I get a smaller number? Oh, 1 over R, 1 over R, 1 over R. So you can kind of, if you double check yourself conceptually, you can make sure you're not getting them confused. But if you studiously learned the capacitances, this is the opposite rule. If, like me, you learned resistances in some other course beforehand, then, you probably know that one better. But don't get them confused. Okay, that's the most common mistake. It's not the math. This is not about math. Yes?
In the previous, where do we get the intensity, or I? In this
I is current. No, in this section, I is current. Yeah. Delta V equals IR.
I is going to be given, right? Can we find this on the...
Oh, I can mess with you as much as I like. I might only give you that EMF, and I might give you those resistances. And I could say, what's the current flowing into the network? Or I could say, what's the current flowing out of the network? Or I could say, what's the current flowing out of the battery? What's the current flowing into the battery? They're all the same. But then I can say, what's the current flowing into R1? I can say, what's the current flowing out of R1? They're both the same. Into R2, out of R2.
They're the same too.
They're the same but different from the R1 and R2 currents are different. So there's a whole bunch of things. And this, one of the issues with this is it's always V equals IR, and it's always R series equals R1 plus R2, or R parallel, 1 over R parallel equals R, 1 over parallel. The equations are all simple, but I can ask you different things.
An EMF, what is it like?
EMF is your driving force. It's the voltage caused by your battery.
So it's there to be, right?
It's measured in volts.
All right.
But that's not necessarily the same as, that's also measured in volts. That's my potential difference, PD across R1, and that is my PD across R2. So, yeah, this is my delta V EMF. There's the same things are used in different ways. So you got to live with these things. You got to do a whole bunch of problems. Otherwise, if you say, I know the equations, I can do it on the day, it's going to be a disaster. You got to practice, 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 practice. It's not simple. It's kind of complicated.
They are different, but dimensional. Let's say they are the same.
Oh yeah, but you got to put different numbers in.
Yeah.
Yeah. So an 8 ohm resistor is connected in series with a 4 ohm resistor. Series means no choices, so there must be end to end. 8 ohms, 4 ohms. What is the equivalent resistance of this circuit? So I want a single circuit. So that is going to be R, I'm going to call it R series, just so I remind myself, because they're in series. R series equals R1 plus R2, that's nice. Or I could put down R8 plus R4, just some way of naming what it is. So R series is equal to 8 plus 4. R series equals 12 ohms. Not bad. Pretty straightforward. 8 ohm resistor is connected in parallel, so does it matter which one's on the left and which one's on the right? As long as you decide, but it doesn't matter. So I say, oh, I want the single resistor. We've got RP in this case. 1 over RP equals 1 over R1 plus 1 over R2. There's a special relationship that you can use for when there's only 2 resistors to get you the answer in one step, but I hardly ever ask you only 2 resistors. So you might as well just get used to, the more fundamental one. So 1 over RP is equal to 1 over 8 plus 1 over 4. Rest is what sums, isn't it? RP is equal to, if you like, it's going to be 1 over 8 plus 2 over 8, which equals 3 over 8. And a whole bunch of people will give me that as the answer. But in fact, RP is equal to 8 over 3, which equals 2.66 ohms. Cool. I'm sorry, I did this last time, and for some reason I copied it onto the original thing, so let's just pretend we've not done this. So, first decision. So you want the one that replaces all of that, and the first decision is, which combination do you do first? And if you try and do the 3 with a 2, or the 3 with the 8, it's ambiguous because these two are unambiguously parallel. But you can't do the 3 with the 8 and ignore the 2 because the 8 and the 2 are kind of in equivalent positions in the circuit. And I don't know right how to put that into words, but you get the feeling for it. So 1 over RP is equal to 1 over 8 plus 1 over 2, which equals 1 over 8 plus 4 over 8, which equals 5 over 8. So RP is equal to 8 over 5. And then I go down here and I go, well, okay, I've got, oh, I'm sorry, I just slipped into the European way of doing these things. I do that occasionally. I have croissants and, you know, stuff like that. But the European way is that you have this little square thing rather than this curly little line, this crooked little line. It's just a little rectangle. But so this is going to be 3 ohms, and that's 8 over 5 ohms. And then I go, okay, I want the 1 to replace it, which is going to be R series in this case. So RS equals R1 plus R2, which equals 3 plus 8 over 5. R series is equal to 15 plus 8 over 5, which equals 23 over 5, which equals 4.6 ohms. Yep. In this one, what I'm doing is, it's really a bad example, because it's still series with 2 parallels, yeah? Upside down doesn't matter. So let's do one that's a little bit more different. So forget that. Bad example. That. So let's do, oh, I'm sorry. I'm going to do this and I'm going to do that one because this was a slightly different thing. So, well, I didn't read the question. I just thought it was another. So let's do that. Find EQ. I'll come back and do that question again. I'll do that again. So let's have a look. Let's make this one 4 and this one 2 and this one 6. So in this one, I want to sort out what order, and in this case I'm going to do the series first because they're unambiguously in series. 2's in parallel with 4, but so is the 6, so do the series bit first. So we're going to go R1 over, oh no, R series equals R1 plus R2, so R series equals 2 plus 6, which equals 8 ohms. So now I have a circuit that looks like this. That's 4 and that's 8. I want the 1 that replaces it. 1 over RP, P is equal to 1 over R1 plus 1 over R2, which equals 1 over 4 plus 1 over 8, which equals 2 over 8 plus 1 over 8, which equals 3 over 8. So RP is equal to 8 over 3, which equals 2.66 ohms. Agreed? Do you notice something about the answer for a series combination? The answer, is it going to be always bigger or always smaller than any of the ones in the series combination? It's always got to be bigger. And by the same token, do you notice something about the parallel combination? The answer is always smaller. So in a parallel combination, your answer is smaller than the smallest value. It doesn't average things, it's getting less and less and less. If you put that second straw there, it's always going to make things easier. And it's going to be easier than any one of them by themselves. So that's a good conceptual thing to have in mind. I'm going to erase that because I want to go back. And it's just, it's not that different. It's just I want to do the next level of complexity. This nice thing about the videotaping is that I can erase. Unfortunately, once I've stored this, one time I must have done save the things for next time, and I couldn't get rid of it. So I got to, okay, so we're back. Come back here. Now let's do the question as it stands. So a 12 volt EMF is applied across a resistor network, and it's this resistor network. So this is 12 volts EMF. And this is the 4 ohms, this is the 2 ohms, and this is the 6 ohms. Now, there's a ton of things I can ask you. I've given you the resistances and I've given you the EMF, so the only things left are, there's 2 other things I can ask you. I can ask you for the potential differences across various parts of the circuit. Let's think in terms of water pressure. Here's my pump. Here's my big pipe. I didn't draw that well, did I? Here's my big pipe. So the first time I went to California, it was back in I don't know, whatever it was, probably 1980s. I noticed they had these big pipes that went from one side of the road to the other. And then, why not? They'd attached traffic lights to them. So I thought, oh wow, they must have the water pipes going over the road because of earthquakes. You know, what do? You take the only thing you know about California and you take this unusual thing and you put them together. So, and for years, I thought these were water pipes because they look like water pipes. And then they started putting them up in Florida, and I said to somebody, oh look, they're putting the water pipes over the roads. And then they said, they're putting the water pipe over every junction where there's, oh, I don't know, traffic lights. And I realized, oh, it's, yeah. So I realized that it was, I guess it was just the next level of sophistication was, oh, I didn't mean to do that. Oh, I didn't mean to do that. That's really nice. So, yeah. So these are like really big water pipes. And then these guys are like our resistors. Now you could put a pressure gauge here. And you could put a pressure gauge there. And say, what's my delta P? That's my drop-in pressure. And I could put my pressure gauge here and my pressure gauge there and say, what's my delta P? And these would be the same. Because the pressure here is the same as the pressure there, pressure there, pressure there, pressure there, pressure there, pressure there, pressure there. Because it's a big fat pipe. There's no pressure drop in big fat pipes. So that pressure there is the same as that pressure there. The pressure here must be the same as the pressure there because that's a big fat pipe. So my pressure drop across this straw, no matter how big or wide it is, my pressure drop across this straw must be the same because they're connected by wires together. Now my pressure drop here must be the same as that guy. That's going to be the same because it's a big fat wire joining them. And then my pressure drop against here, my pressure drop here would be the same as there. This pressure drop will not be the same as that pressure drop because they're in different bits of the circuit. That pressure drop will be the same as that pressure drop. And that pressure drop will be the same as the pump pressure. And if you can get that analogy and live with it for a while, and then recognize that that's like talking about potential differences in EMFs, it really helps. So it's worthwhile spending a bit of time with this analogy. Because on this, I can ask you about the potential difference across there, delta V. 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 I can ask you about those different potential differences. And if I can ask you about those potential differences, I can then ask you about the current flows. So the next thing I can ask you about is the current flow there and the current flow there. And these will not be the same. I call that I system. And I'll call this I4 because it's going through the 4. And I'm going to call this I2 because it's going through the 2. And then this is, what shall I call the current flow through that bit of wire? No, I2, it's just the same. What goes in must come out. And what about this guy?
I4.
I4. And then that guy?
I4 plus I2.
I4 plus I2 is good, but I call it something else. I call it I system. Yeah? And then I system. Can you see how these are not hard? They're just complicated in terms of, it's like you know how to drive. So what do you do to drive from here to the Straz Centre? You've got to figure out the route. It's just because you drive, don't mean to say you're not going to get lost. And that's the problem. You know how to do the equation, you know how to do the math, but will you get lost? That's the problem. Most of the time, I need to clean this up. Most of the time, we are using combinations of resistors to control potential differences. We don't make a circuit very often with only resistors in it. Why would you do that? It's like a total waste of time. If it was a fire, maybe one of these resistors is the element in a fire, then you would, but very unusual. Most of the time I'm trying to light a light or do something. And it turns out that if I put the wrong voltage across a component, I will push too much current through it, or I will cause it to burn out or something. I will blow my speakers in my stereo system if I put too much voltage on them. I will burn out the light if I put too much voltage on it. I will burn out my alarm system if I put too much voltage on it. I've got to get the right potential difference across the right component. And the way I do that is I use a series of a combination. Let's say 12 volts, and I can't have 12 volts across this is my LED. I can't have that voltage across my LED. Let's see, I'm going to change this a bit more. So there's my LED. Oh, that was really good. So that comes down here, through there, goes through there. And we're going to call this this is my LED. It's like I've got a special little symbol. There's my LED. I got to have 7 volts across it. I will put it in combination with other resistors so that there will be 5 volts across there, giving me 7 volts across there. So I'm using my resistors as a voltage regulation system. There's a classic circuit called a voltage potential divider, which is basically this. It's the simplest circuit. You got 12 volts. You want to divide it into 2 6s. Make these resistors equal. doesn't actually matter what resistor you're within reason. If the current doesn't matter, it doesn't matter. I could have 3 and 3 and 4 and 4, or 7 and 7, or 1 and 1. You want to make this into, you want the top one to have 3 volts across it. Simplest way, use a 3 ohm resistor and a 9 ohm resistor. Because 3 and 9 make 12. But either way, well, 1 and a 4 would do it. A 6 and a 24 would do it. As long as the ratio is what you want to what you want to throw away, it will work. It's a beautiful circuit, beautiful little circuit. And after a while, if you live with circuits long enough, you can kind of look at these things and figure out what's going on. Why do you just have these combinations? Because sometimes you don't have the right resistance. So I can put things in parallel to make them less. Let's say in my toolbox I've only got a 6, a 4, and a 2, but I don't want 6 to be ratioed with a 4 or a 2. I want 6 to be ratioed with something smaller. Put the 4 and the 2 in parallel, they become less. There's my ratio. So there's a whole world of playing with circuits. Can I ask a quick question? Just how many people here kind of consider themselves as hobbyists? How many people have a soldering iron and some resistors and go down to, not there anymore, but still like Radio Shack, and had to go up building a buzzer? How many people want to be electrical engineers? Okay, if you want to be an electrical engineer and you're not a hobbyist, go down to Radio Shack and buy yourself a soldering iron and just play. How many people want to be mechanical engineers? You got hacksaw, you got a vice. Get started now. Just do stuff. Go down to Home Depot, buy yourself a whole bunch of PVC piping and build yourself a bridge. You know? And just play with it. You'll get so good and you'll be so far ahead of other people in the class. Because people do engineering because it pays well, when they should be doing engineering because they love it. And if you love it, you're going to go down to Radio Shack and, you know, you could do a lot of things to earn money. Oh, I didn't mean to do that. Yes.
Regarding that last slide.
Okay, I steered myself into Disasterville. Go on. Sorry, yes. Regarding the last slide.
So you talked about ratios. Are those numbers you came up with different ratios?
Let's look. 3 and 9.
One's 1 to 3 and the others are 1 to 4.
Oh, because I messed up.
Okay.
I'm sorry. Because I messed up. It should be like that.
I didn't know if that was like significant.
No. I'm just like my brain cells are going. So what you got to do is you got to take it. It's the one you want over the sum, ratioed with a sum. So that's 3 out of 12.
So it would be like 1 and 3, but where instead of 1 and 4.
Yes, I gotta. If I want 3 volts across there, yes.
Okay, cool.
If I want 3 volts, it's that, or it is 1 and 3 adds to 4, so it's 1 out of 4. And 2 and 8, no. 2 and 6 adds to 8, so it's 2 out of 8. Yeah?
Alright, cool. Yeah, that makes
Is that ratio? Cool. Okay. So that's why we do a lot of this. So as a teacher now, I have some choices. I could ask you about potential differences. I could ask you about currents. And that's the next level of sophistication is, all right, we've got the idea of how we combine things in a network. Now how do we figure stuff out about the network? And there's an awful lot of conceptual understanding. And the other problem I've got is that there are so many ways of getting the same answer that I can just show you examples of how to get there. But there's so many ways. And so you are literally on your own orientating your way through. But I can show you some ways of approaching. So what does it say? It says a 12-volt EMF is applied across the resistor network. What is the current flow through the 2 ohm resistor? So I want my I across my 2. I through PD across. And that's important to learn. I through PD EMF across. Because you see people talking about these things completely wrong. And if you're talking about it wrong, you're visualizing it wrong. So the current goes through a resistor. The potential difference is across the resistor. People talk about the current, talk about the current across or the voltage through, and you can't have that. So just sort of tighten up on that. Make sure you get that. That's what I want. I'm going to try and solve it in one step. Oh, what do I know? Ohm's law. The current through my 2 is equal to the potential difference across my 2 divided by my resistance of the 2. I'm going to use V equals IR all the time. Oh, lots, I mean. Okay. Put in what you know. Oh, I know the 2. So this is delta V2 over 2. That didn't solve it. So let's go down and say, oh, I want to find the voltage drop across here. I can't use V equals IR. I've already used that. So the next thing I use is EMF is equal to my voltage drop across the 2 plus my voltage drop across the 6. Where did that come from? The EMF is spent as potential differences in your circuit. So that's conceptual. I'm saying it's the voltage drop across there plus the voltage drop across there must equal my EMF across there. Why is the 4 not included? Because the voltage drop across the 4 is the same as the voltage drop across the 2. So again, think of the big fat pipe. The pressure of my pump is equal to, if I want to measure the pressure of my pump, I'd measure the pressure across one of those 2 tubes and then add it to the pressure across that tube. Yeah. Okay, so let's have a look. My voltage drop across my 2 is equal to my EMF minus my voltage drop across the 6. Put in what you know. My voltage drop across the 2 is equal to 12 minus my voltage drop across the 6. Man. If only I knew the voltage drop across the 6. I'm going to change pen, sorry. Change color pen. So now I want to find the voltage drop across here. This is my delta V across the 6. Well, I'm back with V equals IR. So I'm going to say delta V6 is equal to my current flow across the 6 times the resistance of the 6. So delta V6 is equal to my current flow across the 6 times 6. Rats! I've still not got it. Okay, but if I knew the current flow across the 6, I could get it. My current flow across the 6, I6, is the same as the current flow through the 12. So my current flow through the 6 equals the current flow in my system. Whoa! I don't know the current flow through my system, and I'm running out of colors. Purple. My current flow through the system is equal to my potential difference of the system over my resistance of the system, which equals, what's the potential difference across my entire system? 12 volts. 12 over R sys. Man! Let's go back to black. Yeah, sorry. Nothing I can do. It's like R sys equals, oh, sorry. Let's work out the total resistance. So the first thing I'm going to do, is combine those guys. 1 over R parallel equals 1 over 4 plus 1 over 2. 1 over R parallel is equal to 1 over 4 plus 2 over 4, which equals 3 over 4. RP is equal to 4 over 3. That's 4 over 3, and that's 6. R series is equal to 6 plus 4 over 3, which equals 22 over 3 ohms. You've got a choice now. You can either leave it in fractions or you can do it in decimals. I'm going to make it into decimals. Very often people leave it in fractions because you're rounding when you go into decimals. But I think it's a bit distracting when you do this stage and you've got fractions flying all over the place. So that is going to be 7.33. We all agreed on that. 7.33? So now I substitute in. So this equals 12 over 7.33. And again, people will let that ride, but I'm going to work out a number. So 12 divided by 7.33 equals, I'm going to get 1.64 equals 1.64 amps. And then I'm going to go back here. So this is going to equal 1.64 times 6, which equals times 6 is equal to 9.82. And that's going to be volts. And then I take that and substitute it in there. And that equals 12 minus 9.82. So that equals 12 minus second answer is equal to 2.18 volts. So I'm going to take that to there. So this equals 2.18 over 2, which equals 1.14. Did I do that? 1.09. 1.09 amps. Mathematically, it's a piece of cake. It's not actually conceptually that hard. It's just long. There's a few things. V equals IR, and you use all your voltages add up to your EMF. That's there's basically three things. There's V equals IR. There's all your voltages add up to your EMF. There's the currents at a junction must equal 0. What comes in must go out. And there's in parallel the EMFs, the potential differences are the same. Yeah, just some conceptual stuff. And the next thing is just it's like peeling an onion. You start by trying to get what you want, and you can't because of this ladder, so you figure out how to find the ladder, and you can't because of this other thing, so you figure out and you just let it unfold itself. And you'll get them right. You will get them right. And I would commend you, especially if you're going to be an electrical engineer, you've got to be able to do these, because this is what bread and butter is about. There are some shortcuts, and the shortcuts are to do with ratios. So, for instance, I could have looked at that top two EMFs, and if I know the potential difference of these two added together, and they're in series, I can do that ratio bit where it's the top resistance over the total resistance will give you the ratio of the potential differences. And the same, we didn't do it in this case, but the same goes for current. Sometimes I could say, if I have 6 amps coming into this junction, if I have 6 amps coming in there, if I have 6 amps coming in here, which one of these resistors would have more current flowing through it? The big resistor will have less current flowing through it because it's a big resistor. So the 2 is going to have more current flowing through it than the 4. And guess what? It's going to be a 2-to-1 ratio because that's the ratio of the resistors. So divide your current into 3 bits. 6 divided by 3 gives me 2 amps. 2 amps goes through the 4. 4 amps goes through the 2. Let's say it was 12 amps coming in. Divide your current into 6 bits. That's 2 per bit. 4 of those bits go through the 2 ohm. 2 of those bits go through the 4 ohm. So you can save time using ratios. But that comes with practice. I would not commend you to start doing that off the bat. Although people sometimes get very quickly. When I ask this question, there's 3 attempts at this question. There's either kind of blank page, or there's something that, there's 4 attempts. There's something that gets it right, and it's like all the steps are laid out. Or there's an attempt that the steps are kind of, people get lost somewhere. Or there's an attempt where it's like all the ratios, boom, 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 and it's like there's hardly any writing down because they've got all the ratios, but they got it right by and large. So don't be put off by it. Take it as a personal challenge and get it right. It's practice. We've got 5 minutes. I just want to set up for next time. Next time, with more complicated circuits. What is a more complicated circuit? A more complicated circuit has several power supplies in it. Sometimes fighting each other. Sometimes resisting each other. Sometimes helping each other. So that would be a more complicated circuit. You can hardly see it, but that would be the more complicated circuit. Because you've got 2 power supplies. Using V equals IR and that would be a real pain. And so along came Kirchhoff, and Kirchhoff basically saw a couple of things. He saw at a junction, the currents in must equal the current out. Imagine you take a road junction and you had more cars leaving than arriving. That would be a really impressive road junction because that means it's a car factory. Or you had fewer cars leaving than arriving. Man, arrest those people because, you know. So that's one thing he noticed was the current in equals current out. And then the other thing he noticed is if you go around a loop, the total voltage sums to 0. What does that mean? It means that EMF added to that potential difference, added to that potential difference, must sum to 0. In common terms, the potential that's created in an EMF is spent as a potential difference. Otherwise, you'd have an accumulated amount of voltage somewhere, and that doesn't happen. So 2 very simple rules, and we use them in a very formulaic way. And what catches people out on this is that you apply these rules, but you're not given much information. So, for example, in this circumstance, well, I've not told you where any current's flowing. I've not told you what the current's called or anything. So I got to name this current. I'm going to call it I1. And I've drawn it going to the right. So I'm going to call this one I2. I've drawn it going to the left, and I'll call this one I3. So I have defined, the law says the sum of the currents at the junction equals 0, but I have to write that down. So I have said that I1 plus I2 equals I3. And if I use different names, or if I use different directions of arrow, I would have a different equation. So when I grade this, the first thing I looked out for is, do you have your direction and names of your currents? And if you don't, you're done. If you do, you get some credit for it. Does the equation match your diagram? And then the second bit, which I want you to just think about, is we have to think about a loop. And the loop has a direction to it. It's an imaginary construction. It's not current. It is an imaginary loop. And it could be a clockwise loop or a counterclockwise loop. And the direction I imagine it changes my equation. So I'm going to put a loop there. And the loop is going in that direction, not the current. And I put a loop there. And the loop is going in that direction, not the current. And yeah, the rule says the sum of the voltages at a junction equals 0. But how do I enact that? And there's some subsidiary little rules. That's positive, that's negative. My imaginary loop is leaving via the positive exit in that battery. It goes through the battery and it's leaving by the positive door. So that's a positive 6 volts EMF. If I'd drawn the loop the other way, it would be a negative 6 volts EMF. So for batteries, you say, what terminal does my loop leave by? And then I say added to, and I'll look at my 3 ohm resistor. I know that V equals IR, so this is going to be I1 times 3 because, look, I put the I1 through it. If my current is going to the right and my loop through that component is going in the same direction, it's a negative IV. So that's a negative IV. We look at this next one. My current is going down and my loop is going down. That would be a minus 7I3 equals 0. There's my second equation. And then my third equation, I've got a minute left. Write down my third equation. What would you write down? See if you can do it. See if you can do it. What is the 9? What is the 5? What is the 7? Can you do it? See if you can do it. If you can do it, that's tremendous. Give you 59, 58, 57. No pressure. See if you can do it. Because if you can do those 3 things, you can do this work. Another 15 seconds. So, let's go. What is my 9 going to be, positive or negative? Negative. How did you know? Your loop is leaving by the negative door. Then we add, because it's a sum, so we add. Now look at your 7 ohms. Doesn't matter which order we do them in. 7 ohms. What's the current flowing through it? I3. It's going to be a positive. Why is it positive? Because the current's flowing down and my loop is going up. And then we had our third one. And third one is going to be about I2 and 5. Current flowing through it is I2. Is that going to be a positive or a negative? Positive equals 0. If you can get that equation, and that equation from this diagram, all the rest is sums. You can do these hard circuits. Very hard circuits to do using Ohm's law. A piece of cake using Kirchhoff's laws. Next time we'll do this.